Good afternoon, everyone, and thank you so much for the opportunity to allow us to introduce you to our Phase 2 submission of C.A.M.I, the Computerized Agriculture Monitoring Interface.
We are Noah Kay and Noah Berlin, and we are currently 8th grade students at West Hollow Middle School in Long Island, New York.
We have spent the last 2 years studying controlled environment agriculture in both our science class and after school coding and engineering club. Our goal is to apply our knowledge of plant science, the engineering design process, robotics, and programming to finding solutions for growing food in alternative environments.
With our ever-increasing world population, erratic climate conditions, and depleting natural resources, we recognize the need to find innovative methods for producing food. As our capabilities for sending manned missions deeper into space continues to grow, we also see our projects having applications for the ISS and beyond. This is the main reason why we refer to our lab as our Mars farm.
We've made use of CAD and 3D printing, electronics, and coding and applied them within our design challenges. It is a space where we have experimented with over 3 dozen species of plants and developed ways to automate their growth through the use of environmental robotics.
For our initial submission, our focus was to bring the projects that we had worked on throughout our lab into a footprint that was comparable to the veggie system currently being used on the ISS. This involved incorporating 18 environmental sensors that could monitor atmospheric and root zone conditions, as well as 11 actuators in the form of peristolic pumps, DC fans, and relay-controlled grow lights and irrigation pumps. We also used a small autofocus ArduCam to run time lapses and have live look-ins on the growing environment. In total, we were able to account for nearly 20 different environmental variables associated with our growing cycles.
Because this project was something that's being scaled down to fit within the unit supplied to us in our Growing Beyond Earth challenge, we also feel it could be scaled back up to meet the needs of a full farm once colonization of extraterrestrial habitat has been accomplished. We understand that the intent of this challenge was to automate the growth of a crop for 28 days without human intervention. However, through our study of growing plants in space and our discussions with experts by presenting our work, we have come to realize how important the care of these crops can be to the well-being of crews on board the ISS. To this end, we have also designed a graphical user interface using Adafruit.io that allows the astronauts to manually control all aspects of the system. By simply toggling from auto to manual mode, they can administer adjustment solutions, initiate feedings, and modify the environment by controlling the fans and photoperiod of the growing lights.
Additionally, the state of all atmospheric and root zone variables can be accessed anytime and from anywhere. We have designed the widgets so that if any variable falls outside of the predetermined set points, they will change from green to red, indicating that that action should be taken. Given that this information is all online, it can be done by the astronauts remotely while on missions, or can be done on their behalf by members monitoring the food from mission control.
For Phase 2 prototype, we made many adjustments to the configuration of the growing area as well as the placement and collection method of our sensors. We completely switched our growing method from soil-based to a deep water culture method of hydroponics. This was due to the fact that we brought a water reservoir into the growing area to meet the space constraints. Given that the success we have seen in our Mars farm, we thought this will also allow for increased root mass that directly accesses the nutrient-rich water sitting beneath the plants.
To simulate the pouches we've been seeing used on the ISS, we filled permeable mesh bags with coconut coir as our growing medium. Once seeded, they were placed in net cups that rested in the lid of the reservoir. A total of 8 sites were equipped with direct injection needles, and moisture sensors were within the system. Our Phase 2 crop was Swiss chard due to the success we have had with it in the lab, as well as the nutritional benefits that come with the antioxidants and vitamins it can offer for the crew.
Another goal that we had was to clean up the sensors and wires within the growing area. Our atmospheric sensors are now neatly passed to the back panel, and the wires are now routed across the top of the reservoir and out through the cable gland sitting behind it. They've also placed a Raspberry Pi touchscreen at the top of the unit so the crew members can interact directly with the system to determine thresholds and set points.
The biggest change in our Phase 2 prototype can be seen on the back of the unit. We created a 2-level fertigation manifold that serves to check water quality and make any necessary adjustments. The top level includes all of our root zone sensors, which take more accurate readings as a stream of water passes across them. In the second level, you will see inlets for 6 different adjustment solutions that are distributed to the reservoir by way of peristaltic pumps controlled by an Adafruit motor hat. The housings for these pumps and the solution containers were designed using Fusion 360 and 3D printed using PLA. Based on the readings from the pH sensor, the first 2 pumps administer acid and base solutions to maintain a pH range between 5.5 and 6.
Our program included timer construction state flags that allowed for the EC of the system to be walked up incrementally to a target of 1.4 by the end of the 3rd week. 3 pumps were used to distribute an A and B growing solution, along with a calcium-magnesium supplement. Feedings are added on the 7th, 11th, and 14th of the month.
The final pump was included as a precautionary measure in the event the ORP reading fell too far below our target of 400 millivolts. If the root zone environment showed signs of unwanted microbial content, a single dose of hydrogen peroxide was to be administered. We are aware of how sterile the system must be for use on the ISS, but we also did not want to damage the fragile roots of the plants growing above. Fortunately, this measure proved unnecessary during our growth cycle for Phase 2.
In addition to testing and treating the nutrient solution, this circulation system was meant to keep the reservoir continually mixed and oxygenated. The pumps that circulated the water and injected into the root zone of the plants were controlled by relays, triggered by the Raspberry Pi's GPIO pins. We also included an inline flow meter to ensure that this system was operational and adjustments would be possible. Aside from a small leak in the seams of the manifold early on that was cured with silicone, this system operated as intended throughout the duration of growth cycle.
We have 2 main communication protocols for our sensors. Our first takes advantage of the simple wiring that I2C sensors offer. These addressable sensors monitor water temperature, electrical conductivity for nutrient adjustment, oxidation reduction potential to ensure unwanted microbial growth is kept to a minimum, pH and dissolved oxygen of the nutrient reservoir. Carbon dioxide, temperature, and humidity levels are monitored in the canopy area. Luminosity and mixing rate by way of an inline flow meter create closed-loop systems that ensure that our circulation and lighting systems have not failed. We had to include an external analog-to-digital converter for some of our sensors, as the Raspberry Pi does not have the ability to make analog readings. To calculate soil moisture, we used an array of 4 capacitive moisture sensors that each take an average of 20 readings every 10 minutes. This allows the system to know when to administer direct injection of water and nutrients into the root zones of the plants.
Vapor pressure deficit is a variable that we were interested in monitoring in order to control the rate of transpiration for the plants growing in the chamber. In Phase 1, we used thermistors that were attached to the underside of the leaves in order to monitor leaf temperature. We used this data and compared it to relative humidity and air temperature surrounding the canopy to calculate the vapor pressure deficit. Once we realized that we could not touch the plants in Phase 2, we switched to the leaf temperature monitoring over to no-touch IR sensors that were attached to the top of our reservoir. The inspiration from this came from all of the no-touch temperature scans that we've seen being taken in the world around us every day.
We had a target VPD of 0.7 to 0.8 in mind, but the system would not take action unless the VPD fell below 0.2 or rose above 1.4. Under these conditions, an exhaust fan would evacuate the air in the chamber to help lower the relative humidity to increase the VPD. If the VPD became too great, the intake fan would turn off in hopes of slowing the rate of transpiration.
In order to keep the cost of equipment down in Phase 2, we switched our pH, ORP, and DO sensors over to analog readings instead of using the more expensive I2C integrated chips. This required us to add a second ADC as well as isolation circuitry to avoid electrical interference from the pumps and sensors in the reservoir. We also had to derive equations that converted the analog voltage output of the sensors to real-world environmental readings. Luckily, Atlas Scientific provides excellent documentation that helped us with this effort.
Plants were started in the system on May 21st and harvested on June 17th. The average mass per plant was roughly 1,400 milligrams, giving us a total edible mass in our final harvest of 120,000 milligrams. We feel we could have promoted a higher yield had we pushed the nurturing plants with nutrients a bit earlier. We waited for 2 weeks before administering nutrients into the reservoir in an attempt to prevent burnout of developing seedlings, which could have kept us from having any results to report.
We were really inspired by the presentations of the collegiate teams in this challenge. This summer, it is our goal to develop computer vision and machine learning capabilities in our system. We are hoping to use the camera that we mounted just under our grow lights to be able to conduct a color analysis of the leaves in order to monitor general plant health and identify potential nutrient deficiencies. We would also like to be able to accurately measure the size of developing plants within the system in order to predict and optimize growth rates for future crops.
We would once again like to thank Fairchild Botanical Gardens for the opportunity to take part in this challenge. As young engineers, we have had so much fun developing our skills and applying them to something we were already very passionate about.
We also appreciate all the valuable feedback we have received from the scientists at NASA and participants in this program. We tried our best to incorporate your suggestions into our Phase 2 submission.